right now, the AI model that's writing your emails or, compiling your code, it's quietly boiling away millions of gallons of municipal drinking water.
Yeah, literally millions.
Exactly. And the digital cloud we all rely on isn't some ethereal mist floating above us. It is incredibly stubbornly physical.
It really is.
It's heavy, it runs blazingly hot, and frankly, we are rapidly running out of land to put it on.
Yeah,
So, welcome to the Deep Dive.
glad to be here.
Today, we're looking at a single, incredibly detailed report about a massive pivot in how we actually sustain the digital world. The mission for us today is to deconstruct this highly capitalized, radically engineered solution that takes the heaviest computing infrastructure on Earth, completely severs its physical ties to land, and, well, plunges it directly into the open ocean.
It's an absolutely fascinating text. I mean, it demands that we completely reframe our basic understanding of infrastructure. Because when we talk about the physical architecture of the internet and artificial intelligence, my core belief and the lens I really want us to use today is that true paradigm-shifting innovation almost never happens when you just try to optimize a broken legacy system.
Yeah, that makes sense.
You don't trigger a revolution by making a terrestrial data center, 3% more power efficient. You get it by entirely abandoning the constraints of the land and completely changing the environment.
Okay, let's unpack this, because to grasp why a company is literally dropping server racks into the Pacific, we really have to look at the terrestrial breaking point driving them off the continent in the first place.
We do.
Because the source outlines this cascading series of existential constraints hitting land-based data centers right now. We're talking limited grid capacity, cooling water scarcity, supply chain bottlenecks, and just severe permitting delays.
Right, and these aren't just, isolated headaches for tech executives.
No.
They are massive physical roadblocks that are halting the expansion of AI. What's fascinating here is how these constraints mathematically compound one another.
How so?
Well, take grid capacity. We aren't just talking about plugging in a few more servers. We're talking about modern AI data centers demanding anywhere from 300 to 500 megawatts of continuous power.
Wow, 300 to 500.
Yeah. That is the equivalent energy draw of a medium-sized city, all concentrated into a single warehouse.
That's insane.
It is. And the local power grids simply were not built to handle point loads of that magnitude. When a tech giant requests a 500-megawatt hookup, the utility company has to build entirely new high-voltage transmission lines and, massive substations.
It's going to take forever, right?
Exactly. The supply chain for high-voltage transformers right now has lead times stretching into the years. So you hit a hard stop on energy availability, it just becomes a localized zero-sum game.
And the power problem immediately creates the thermal problem, right? The second constraint our source really hammers on is cooling water scarcity. And this is where the physical reality of computation gets incredibly messy.
Oh, absolutely.
Because computing is, at a basic thermodynamic level, just the process of turning electricity into heat.
Exactly right. When you push hundreds of megawatts of electricity through dense arrays of high-performance silicon, that energy doesn't just, vanish. It is entirely converted into waste heat.
Right.
And if you don't remove that heat instantly, the microscopic silicon pathways literally melt. They just degrade. So to manage this thermal load, terrestrial data centers rely heavily on evaporative cooling towers.
Which use massive amounts of water.
Millions of gallons. They pump in municipal freshwater, run it through heat exchangers, and evaporate it into the atmosphere just to pull the heat away from the servers.
Which puts the data center in direct competition with the community it's actually built in. You have a single facility drawing down both the local power grid's maximum baseload and the local water reservoir.
Yeah, it's a huge strain.
And the source specifically highlights the fallout from this, noting that residential communities are actively organizing, legally and politically, against new data center construction.
And rationally so. I mean, the communities are experiencing all the immediate localized downsides of global AI infrastructure. The report specifically notes increased utility costs, noise pollution, and the diversion of public resources.
Right, because when an entire region's grid is strained to its absolute limit to feed a data center, the utility provider inevitably passes the costs of those grid upgrades down to the residential ratepayer.
Exactly. Plus, they have to live with the noise. It's not just the visual blight of a giant concrete bunker.
Yeah, it's the noise.
It's the continuous low-frequency roar of industrial HVAC systems and massive chiller units running 24/7.
You know, it reminds me of how we view the heavy industrial factories of the 19th century. Back then, you had these massive, resource-hungry textile mills or steel plants that just pumped out smoke and completely monopolized the local river.
That's a really good comparison.
Right. And urban planning eventually pushed those factories far away from residential zones because they were just terrible neighbors. Today, the smoke is invisible heat, and the localized damage is a grained water table and a deafening acoustic hum. We are treating modern AI data centers like heavy industrial blights because physically, that is exactly what they are.
That is an excellent framework for understanding this shift. I mean, the societal benefit of the 19th century factory was mass-produced goods, but the localized cost was pollution.
Exactly.
Today, the societal benefit is advanced artificial intelligence and biological modeling, but the localized cost is resource monopolization. Why should a municipality's limited freshwater reserves go toward cooling an enterprise AI cluster rather than providing drinking water or, agricultural irrigation for the people who actually live there?
Right. It's an unsustainable civic tension, which means the traditional land-based model of building bigger concrete warehouses is fundamentally choking on its own growth.
It really is.
Permitting delays are stretching from months into years as local zoning boards fight tech companies tooth and nail. So, if the land is tapped out, the grid is maxed, and the neighbors are hostile, where do you put the physical hardware that runs the digital world?
Well, you take it where there are no zoning boards, no strained municipal grids, and no residential neighbors. You take it to the open ocean.
Enter Panthalassa. Our source details this U.S.-based tech startup that recently secured a highly strategic $140 million Series B investment round.
A massive round.
Huge. And their thesis is to evade regional regulatory and environmental obstacles entirely by deploying self-propelled autonomous maritime data platforms. They are literally putting the servers on ships.
Yes.
And there's a quote in the source from the co-founder and CEO of Panthalassa that lays out the raw physics of this pivot. He says, and I'm quoting here, there are 3 sources of energy on the planet with tens of terawatts of new capacity potential: solar, nuclear, and the open ocean.
We really need to analyze that statement carefully, because placing the open ocean in the exact same heavyweight category as nuclear and solar is a radical reclassification of global energy resources.
It really is.
Solar and nuclear have dominated the clean energy conversation for decades. But the source makes a very deliberate distinction here, noting that terrestrial renewables like solar and wind are fundamentally weather-dependent.
Right, and as we know, AI workloads don't care if it's cloudy or if the wind died down. They can't rely on intermittent power.
Precisely. You cannot power a 500-megawatt AI training cluster with intermittent energy without an impossibly large and expensive battery storage facility attached to it.
Which just doesn't exist at that scale.
No, it doesn't. AI requires continuous, massive baseload energy. Nuclear provides phenomenal baseload. But, as we know, commissioning a new nuclear plant involves decades of regulatory review, massive capital expenditure, and intense political friction.
Right, nobody wants one in their backyard.
Exactly. The open ocean, however, operates on a completely different mechanical reality. Water is roughly 800 times denser than air. So the kinetic movement of the deep ocean, the swells, the waves driven by distant weather systems, and gravitational pull never stops.
It's just constant.
It is a continuous, incredibly dense, around-the-clock source of kinetic energy.
So they are looking at the ocean not as a shipping lane, but as an untapped terawatt-scale battery that just never depletes. And the capital markets clearly agree with them. I mean, $140 million Series B isn't seed money for a science fair project. That is heavy commercialization capital.
It absolutely is.
But the source explicitly details how they're deploying this capital, and it notes they're completing an assembly facility near Portland, Oregon, to mass produce these autonomous platforms from plate steel in coastal factories.
Plate steel in coastal factories. That is the defining pivot of this entire operation.
Right. And here's where it gets really interesting. Think about the cultural aesthetic of Silicon Valley. We are used to software development being asset-light. Clean rooms, server virtualization, guys writing code in a coffee shop.
Yeah, very clean.
But plate steel in coastal factories, we are talking about heavy shipyards, welding, dry docks. This implies that the bleeding edge of the AI boom is going to look a lot more like World War II naval manufacturing than an app startup. Is the future of tech basically just a return to heavy maritime industry?
Absolutely. The era of asset-light tech innovation is over because the software has finally outgrown the hardware's physical footprint.
Wow.
To capture terawatts of dense kinetic energy from the ocean, you cannot use delicate materials. You need sheer mass. You need durable marine-grade alloys. You need shipyards capable of moving thousands of tons of metal.
Right.
The Pacific Northwest, with its deep history of naval and maritime manufacturing, perfectly positions them to leverage existing heavy industrial infrastructure. The algorithms running on these chips might be the most sophisticated ephemeral math ever conceived, but the vessel keeping them alive is going to be forged from the grittiest, heaviest coastal manufacturing we have.
So we know they're building these massive floating steel islands. But dropping millions of dollars of highly sensitive silicon into the most hostile environment on Earth seems, well, it seems completely counterintuitive.
It does sound crazy at first.
How exactly are these platforms generating power? And more importantly, how are they surviving? The source outlines that the onboard mechanical systems generate clean electricity by converting the kinetic movement of waves into a steady electrical supply.
Right, and this is the critical engineering hurdle. The ocean is serving a dual, highly synergistic functionality here. First, it is the primary engine. While the source doesn't detail the exact proprietary schematics of their wave energy converters, the physics of maritime energy extraction usually rely on the relative motion of the ocean's surface. As the massive steel platform rides up and down on a swell, that immense vertical kinetic energy is captured often through hydraulic rams or oscillating water columns and used to drive an internal generator.
Ah, I see.
Because water is so dense, a relatively small physical movement generates a massive amount of torque. That torque is converted directly into the continuous electrical current needed to power the server racks.
And the second function of the ocean?
The second function solves the thermal crisis we discussed earlier. The source explicitly states that the surrounding ocean acts as a perpetual thermal sink.
A perpetual thermal sink.
Yeah.
Okay, that solves the municipal water crisis, but let's look at the physics of it. What does that actually mean?
Well, in thermodynamics, a thermal sink is an environment that absorbs heat. A perpetual thermal sink is a body so incredibly massive, like the Pacific Ocean, that it can absorb an effectively infinite amount of industrial heat without raising its own baseline temperature.
Oh, wow.
Remember, the millions of gallons of freshwater terrestrial data centers evaporate just to keep the chips from frying? Panthalassa eliminates that completely. They use the deep ocean itself. The source specifically notes that this natural cooling architecture maintains optimal chip temperatures and slows hardware degradation without consuming municipal freshwater.
And that hardware degradation is critical. We aren't just talking about your laptop getting warm on your knees. Enterprise AI chips are incredibly expensive. And at a microscopic level, they're highly vulnerable to thermal cycling.
Yes, electromigration.
Right.
If a high-performance chip operates at too high a temperature, or if its temperature wildly fluctuates, the actual metal atoms within the microscopic wiring of the chip begin to migrate and break down.
So the hardware literally destroys itself.
Exactly. By submerging the heat exchangers into the deep, continuously cold currents of the ocean, Panthalassa achieves an unbelievably stable thermal environment. They have created a perfectly closed-loop system. The kinetic energy of the ocean powers the calculation, and the thermal mass of the exact same ocean instantly absorbs the resulting heat.
It's an incredibly elegant physical loop. But let me push back here, because if you're listening to this and thinking, wait a minute, saltwater and microchips are a notoriously disastrous combination, you're entirely right.
Oh, yeah. Saltwater destroys everything.
Right. If the ocean is this phenomenal infinite battery and coolant, why hasn't everyone moved offshore already? Saltwater is highly corrosive. You have biofouling barnacles, algae that will coat any heat exchanger you put in the water. How are they not just building billion-dollar artificial reefs that rust out in 6 months?
That is the exact friction point of maritime engineering, and it's why it has taken this long to develop. The source mentions their decade of field tests, which we'll get to. But fundamentally, surviving the ocean requires isolating the computing environment from the corrosive environment.
Okay, so how did they do that?
The servers themselves are hermetically sealed within the hull, likely bathed in a dielectric fluid or a highly controlled inert gas environment.
So they never touch the air or the water.
Never. The heat is transferred through specialized marine alloy bulkheads, likely utilizing materials like copper-nickel or advanced titanium alloys that resist biofouling and saltwater corrosion. You don't expose the servers to the ocean, you expose the heavy metal heat exchangers to the ocean, and keep the interior environment perfectly pristine.
Okay, that makes sense. The ship takes the beating, and the servers stay in a clean room inside. But that brings us to the most glaring logistical question. You can have all the free energy and infinite cooling you want sitting 100 miles offshore. But a data center is completely useless if it cannot rapidly communicate with the client on land. And the source explicitly points out that these platforms do not use undersea cables to send electricity or data back to coastlines.
Right, and if we connect this to the bigger picture of infrastructure, we see the true genius of their architectural departure. Historically, offshore energy, like a massive offshore wind farm, has one singular goal: generate electricity at sea and pipe it back to the terrestrial grid via massive, expensive, submarine, high-voltage, direct current cables.
That's incredibly inefficient, right?
Highly inefficient. Transporting raw electricity across vast distances results in massive line loss. As electrons travel through a hundreds of miles long copper cable, a significant percentage of that energy bleeds out as heat due to the physical resistance of the wire.
Oh, yeah.
Panthalassa sidesteps transmission loss entirely. They don't try to move the massive ocean power to the terrestrial computers, they move the computers to power. By running the hardware directly at the point of generation, immediately on board the Maritime platform, they consume the electricity at its source. Zero transmission loss.
Okay, but if they sever the physical core to land, how does the data actually get back? I mean, if I ask the AI to run a massive protein folding simulation and the servers calculating it are floating untethered in the Pacific, how do I get the results?
Satellites.
Right. The source explains that to communicate, the platforms rely on low Earth orbit satellite networks to receive incoming commands and broadcast back what they call completed AI inference tokens.
Yes. This specific mechanism, the completed AI inference token, is the linchpin of the entire business model. And to understand why this works over a satellite connection, we have to look at the disparity in data weight.
Right, because anyone who has used satellite internet during a heavy rainstorm knows latency and bandwidth can be incredibly finicky. How do you run enterprise-grade AI over a satellite bounce?
You do it by fundamentally separating the heavy data from the light data. As anyone working in this space knows, there is a massive difference between the training phase of an AI model and the inference phase.
Explain that for a second.
So, training requires moving petabytes of raw data, entire libraries of human knowledge, massive video repositories into the cluster. You cannot do that over a low Earth orbit satellite.
Yeah.
The bandwidth simply isn't there.
Right.
But Panthalassa isn't necessarily focused on the massive data pipelines of training. They're focused on the output, the inference.
So the prompt comes in, the heavy calculation happens locally in the ship, and just the answer goes out.
Exactly. The calculation required to generate an answer, the inference burns terawatts of energy and generates massive thermal loads. But the resulting answer, the output JSON packet, it is incredibly lightweight. A few kilobytes of text, maybe a few megabytes for an image. That is the token.
It's the difference between shipping a lumber mill the entire forest versus just asking them to mail you back a single carved chair. You send a tiny, lightweight instruction like carve a chair, and the massive heavy lifting, the loud saws, the massive energy burn all stays localized at the mill, and they just ship out the final lightweight product.
That is a perfect mechanistic analogy.
Yeah.
The prompt goes up to a satellite constellation, beams down to the autonomous platform. The kinetic ocean drives the generators. The ocean water cools the chips. The silicon churns through billions of parameters. And the final tiny data packet, the completed inference token, is beamed right back up to space and down to the client's terrestrial office.
And the local power grid, back in the client city, didn't register a single watt of demand.
Nope.
The local reservoir didn't lose a drop of water. The entire physical burden of that intense computation was totally offloaded to international waters.
They have successfully decoupled the massive physical energy requirement of AI from the lightweight data transmission of its output. It is a stunning architectural achievement.
Which brings us to the reality of the timeline. Because on paper, decoupling compute and offloading it to floating, satellite-linked nodes sounds incredible. But is this actually happening, or is this just an incredibly well-funded white paper?
It's happening.
Right, the source provides a remarkably detailed development timeline.
And this timeline is vital because it dispels the notion that this is a sudden, speculative hype grab. This technology has been quietly gestating in the ocean for a decade. The source documents that Panthalassa has already conducted oceanic field tests with preliminary designs. They had the Ocean 1, Ocean 2, and Wade Hopper variants in the water as early as 2021 and 2024.
The progression of those tests is really telling, too.
Yeah.
The source notes that the 2021 and 2024 tests were explicitly designed to verify the stability of its power generation and navigational software.
Yes, they were testing the brute physics before they ever loaded a production server rack. As you mentioned earlier, the ocean is violent. Before you risk enterprise-grade silicon, you have to prove the platform won't capsize in a Pacific gale.
Absolutely.
You have to prove the navigational software can maintain station keeping without a physical anchor, using localized thrusters to fight the currents. And crucially, you have to prove that the wave energy converters produce clean, highly conditioned power. AI chips cannot handle voltage spikes. The electrical output from the kinetic waves must be perfectly smoothed.
So they spent years making sure the hull floated, the rust was mitigated, and the engine produced clean power. But now, they are shifting from physics to production. The source states that later this year, in 2026, they are deploying the Ocean 3 pilot series in the Northern Pacific. And the stated goal for this deployment is entirely different. They are going out to process active computing workloads and standardized manufacturing protocols.
They are moving from prototype to assembly line. Processing active computing workloads means they're fully integrating the server racks and linking them to the commercial satellite networks. But the phrase standardizing manufacturing protocols is the most aggressive part of that update.
Right. Standardizing manufacturing protocols means you are locking in your supply chain to stamp these things out. And that leads to the timeline detail that really stunned me. So Ocean 3 pilots this year, 2026. But the source explicitly states that widespread commercial availability is slated for 2027. So what does this all mean? We are looking at a jump from a pilot program to widespread commercial rollout in 12 months.
The audacity of that timeline indicates that the core physics problems, the hull integrity, the wave-to-electricity conversion, the thermal sinking, have already been definitively solved during the 2021 and 2024 testing phases.
Wow.
The 2026 phase is merely about operational scaling. It implies that the plate steel assembly facility in Oregon is already spun up. They aren't handcrafting bespoke prototypes anymore. They are preparing a heavy manufacturing pipeline.
If they actually hit that 2027 target, we are looking at fleets at these platforms in a matter of months. This isn't some speculative 2035 climate tech goal. By the end of next year, a significant portion of our enterprise AI infrastructure could be physically detached from the North American continent.
And once that template is proven commercially viable, it becomes the new standard. The economic incentives are simply too massive. The company that doesn't have to wait 3 years for a terrestrial grid upgrade and doesn't have to fight local zoning boards will outpace any terrestrial competitor. We are watching the birth of a decentralized maritime compute infrastructure.
It is a phenomenal engineering triumph. We've covered the breaking point of the land, the kinetic mechanics of wave power, the thermodynamics of the ocean as a heat sink, and the lightweight logic of satellite inference tokens. But before we wrap up this deep dive, we have to look at the broader implications of what this actually means. And this is where the conversation shifts from engineering to something much more complex.
It does, and this raises an important question, one that the source hints at but leaves largely unexplored. There is a specific line. High-performance computing is moving into international waters.
Yeah.
We have spent this entire discussion marveling at the mechanical brilliance of untethering data centers from the land. But we must look at the geopolitical and legal reality of what it means to put the world's most critical infrastructure into the open ocean.
Because artificial intelligence is no longer just a consumer product. It is the core intellectual infrastructure of the 21st century. It is driving financial markets. It is modeling pharmaceuticals. It is the backbone of modern defense logistics. It is sovereign-level technology.
Precisely. Right now, if a hyperscale data center is located in Virginia or Frankfurt or Tokyo, it is physically anchored within the sovereign territory of a nation-state. It is subject to that nation's laws, its environmental regulations, and crucially, its data localization mandates and security apparatus.
Right.
If a server farm is in Virginia, it is protected by the United States government, and it is subject to U.S. jurisdiction. But Panthalassa is moving this infrastructure into international waters. They are operating on the high seas.
And the high seas are governed by a totally different set of rules. You're talking about the UN Convention on the Law of the Sea, Once you move past a nation's 12-mile territorial limit, or even outside its 200-mile exclusive economic zone, you are in the Wild West.
You are, and the implications are staggering. First, consider the regulatory arbitrage. A company operating an autonomous AI node in international waters is theoretically immune to domestic terrestrial regulations regarding energy consumption, carbon taxation, or even localized data privacy laws.
Oh, wow. Hadn't even thought of that.
Right. How does a law like Europe's GDPR function when the silicon processing the data is floating in the deep Pacific, flagged to a completely different maritime jurisdiction?
And beyond the legal gray area, there is the raw physical vulnerability. If this technology scales as predicted, you will have the most vital, economically dense computing hardware on the planet floating autonomously hundreds of miles from the nearest coast. No physical fences, no terrestrial security guards, just a steel platform and a satellite uplink.
Which turns them into immediate strategic targets. In a geopolitical conflict, you wouldn't need to launch a cyber attack to take down an adversary's AI capabilities. If their compute nodes are floating in international waters, untethered and legally ambiguous, they are physically vulnerable.
Just literally vulnerable to physical attack.
Exactly. Sabotage, signal jamming, or even maritime interdiction become very real threats to digital infrastructure. The very thing that makes Panthalassa's design so brilliant, its complete independence from the terrestrial grid, also strips it of the terrestrial protections of the state.
It fundamentally changes the map of global power. For a century, geopolitical power was tied to controlling land, controlling oil reserves, controlling physical borders. Now, if the cognitive engine of the future economy is decentralized and floating in the global commons, who truly commands it?
It's an incredible paradox. To save our terrestrial resources, we have to exile our most advanced technology to the most ungoverned space on the planet.
It is the ultimate decentralization. We are solving the physical constraints of the land, but in doing so, we are opening up a massive, unresolved frontier regarding the sovereignty and security of human knowledge. Who truly controls the cloud when the cloud is a steel platform in the deep ocean? That is a profound and frankly somewhat unsettling reality to leave you with. We've spent so long thinking of the digital world as something invisible and infinite, but it has a physical weight, a temperature, and a location, and very soon that location might just be a coordinate in the deep Pacific. Thank you so much for joining us on this deep dive. We hope you walk away seeing the physical reality of our digital infrastructure entirely differently. Keep questioning, keep exploring the mechanisms behind the technology we take for granted, and we'll see you next time.